Bismillahirrahmanirrahim. I am Riaz Hussain Junaid, and I am delivering the video lectures for the course of Applied Electricity and Electronics. The course code is CEE103. This course is being offered by the Department of Electrical and Computer Engineering, Kamsad University, Islamabad, Wye campus for the semester of fall 2020. This is a series of lectures, and today we are going to discuss lecture number 13, and today's topic is problems on Wye-Delta transformations. This course is being offered for the program of Bachelor of Science in Civil Engineering, BS Civil Engineering for the semester of fall 2020. Previously, we have discussed the theory of Wye-Delta transformation, that how we can convert from Y networks to delta networks and vice versa. We have also seen some examples, and in this today's lecture, we are going to apply those techniques on the circuits, that how we can find the equivalent resistances and how we can solve the certain circuits using Y delta or delta Y transformations. Again, for the students information, these video lectures and slides are being prepared from the textbook of Fundamentals of Electric Circuits. The author is Alexander Sadiko, and we are discussing chapter number 2, that is methods of analysis. So let's start the today's lecture. So problem is that obtain the equivalent resistance RAB for the circuit shown and use it to find the current I. This is a circuit given, and we want to find the resistance in terminals A and B, and also want to use that resistance to find the current I, that is the current supplied by the 120 volt source. You can see that this is a simple resistive circuit. Important point is that there is no resistance in either series or in parallel with any of the resistances. Just like 10 ohm resistance is not in parallel or in series with 12.5, because this point is common in between the resistances, but this is obviously different. Similarly, 15 and 20 are not in parallel. Similarly, 30 and 20 are neither in series nor in parallel. So this means that we cannot use the techniques that we developed for the series or parallel circuit. That is, we cannot use voltage divider or current divider directly in this circuit, but we can observe that there are some delta networks and star networks present in this circuit. Just like we have one delta, that is from node C to N and then B. This is a delta network. Similarly, this is another delta network from node C to N to A. Similarly, we have a Y network, that is A, N, B and C. That is Y network consists of 5, 10 and 20 ohm resistances. Similarly, there is another Y network that is that consists of 12.5, 5 and 15 ohm resistances. And also we have another delta network that is actually consists of 10, 30 and 20 ohm resistances. So this means that when we can use the star delta or Y delta transformation to simplify the circuit, and then we can see that how further we can make some simplification. So let's start. There are two Y networks and three delta networks, just like we mentioned here. So let's convert the Y network comprising 5, 10 and 20 ohm resistances. Select R1 is equal 10, R2 is equal 20 and R3 is equal 5. So this is R1, R2 and R3. So this means that we will be converting this Y network into corresponding delta networks. So we can use the equations for Y to delta networks. We know that RA, that is first resistance in the delta network, actually R1 R2 plus R2 R3 plus R3 R1 divided by R1. So we can simply plug the values. R1 is 10, 10 multiplied by 20 plus 20 multiplied by 5 plus 5 multiplied by 10 divided by 10. So this is 35 ohms. Similarly, RB will be equal to R1 R2 R plus R2 R3 plus R3 R1 divided by R2. So this is 350 divided by 20, because R2 is 20. So this will be 17.5 ohms. Similarly, we can compute RC. So RC will be equal to R1 R2 plus R2 R3 plus R3 R1 divided by R3, because we are going to compute RC. So in denominator there will be R3, numerator in each case is the same. So this will be 350 divided by 5. So this is 70 ohms. So now we have RA, RB, RC. That is, now we have converted this Y network into corresponding delta network. So now we can replace this Y network with corresponding delta networks whose resistances are these. So now the equivalent circuit will look like as shown. So now we have actually removed the first of all, because we want to compute the resistance. So obviously 120 voltage source will be disconnected. So we have terminals A and B. Since we have not simplified 12.5, 15 and this 30 ohm resistance, so these resistance will be intact. It means that these will not be changed, only this network will be replaced by the delta network. So this is the actually replaced our equivalent network. So we have actually one point here. So here in here we have a 35 ohm resistance. This is RA, and this is actually RB, and this is RC. So now you can see that since we have converted the Y into delta, so now we can simplify certain resistances. First observation you can make, that is 30 and 70 are now in parallel. So we can combine these resistances. Similarly, 17.5 and 12.5 are in parallel, and 15 and 35 ohm resistances are in parallel. So we can combine these two and these two. So let's continue. Now we can see that 70 is in parallel with 30, so their equivalent will be 70 into 30 divided by 70 plus 30, so this will be 21 ohms. Similarly, we can see that 12.5 is in parallel with 17.5. This is 7, not 7.5, this is 17.5. So again, this will be 12.5 multiplied by 17.5 plus divided by 12.5 plus 17.5. So this is 7.29 ohms. Similarly, we can see that 15 and 35 ohm resistances are in parallel, so their equivalent will be 15 into 35 divided by 15 plus 35. So this is 10.5 ohms. So now we can simplify this circuit. So resulting circuit will be like this. So now we have actually resistance, that is equivalent resistance of 12.5 in parallel with 17.5. This is 7.292 ohms, and then 35 and 15 when combined in parallel, this will be 10.5, and resulting resistance of 30 and 70 in parallel is 21. So now we have this equivalent circuit. So now you can see that obviously this resistance and this is in series, and result is in parallel with 21. So we can say that RAB, that is resistance across terminals A and B, will be called series resistance in parallel with 21 ohm. So the 7.29 plus 10.5 in parallel with 21. So we can easily solve. Again, remember this will be product divided by sum. So this is 9.63 ohms. So now we can easily find I will be equal to, that is current in the main branch. Here obviously this is the voltage across A and B divided by resistance across A and B. So voltage across A and B is 120, and resistance across A and B terminals is 9.63. So current from A to B terminals will be I is equal to Vs divided by RAB, that is 120 divided by 9.63. So this is actually 12.458 amperes. So now we have found this actually current in the main branch. So you can see that delta star transformation could be useful in certain circuits. Let's see another example. For the bridge circuit, find RAB and RI. So this is a famous circuit. This circuit is used to determine the unknown resistance, and the reason behind the point that why this circuit is known as a bridge circuit. So anyway, We have a circuit 220 volts, a single voltage source is applied across terminals A and B. So we want to find resistance in between A and B. Remember that to find the resistance A and B, we have to remove this voltage source, and then we have to connect ohm meter across these two terminals. So the reading in the ohm meter will be actually a resistance across A and B terminals. Again, you can see that there is no actually resistance that is parallel or in series with any of the other resistance. 20 ohm is not in parallel with 40 ohm, neither in series. Similarly, 10 100 ohm is not in parallel with 60. So we cannot use series and parallel circuit techniques, but we can see that there's a delta here. This is a delta, that is 60, 40 and 100 ohm form a delta. Also there's another delta network here, that is 48 and 40 and 20 ohm resistance, and we have also a Y network, that is 20, 40 and 100. This is a Y network or star network, or we have another network that is 48, 40 and 60 ohm resistance. This is also Y network. So we can convert the lower delta, that is 60, 40 and 100 ohm delta into Y networks. So we can see that this is actually 40, 60 and 100 ohm consistent. This network consists of pi or delta network. So we can select RA is equal to 100, RB is equal to 60 and RC is equal to 40. So we can compute R1. R1 will be equal to RB RC divided by RA plus RB plus RC. So in this case, this will be equal to, we have value of RB 60 multiplied by 40 divided by 100 plus 60 plus 40. So this is 12 ohms. Similarly, we can compute R2. So R2 will be equal to RA/RC divided by sum of the resistances. So this is 20 ohms. Similarly, we have R3. This is RA/RB divided by RA plus RB plus RC. So this is 100 multiplied by 60 divided by 100 plus 60 plus 40. So this is 30 ohms. So now we have converted this delta into corresponding Y network. So we can replace that actually delta with corresponding Y network. So now we have actually here R1. This is actually R2 and R3, because we have used this circle light 60, 40 and R, since R1 is, in fact RA is 100, then 60 and 40. So we have replaced this circuit using that sequence. So this will be the resulting circuit. Now you can see that this 12 ohm resistance is in parallel, in fact in series with 48, and this 20 is in series with this 20, and the resulting are equivalent of these two, and these two is in parallel with the other with each other. So we can see that 48 plus 12 is in parallel with 20 plus 20. So this will be 50 multiplied by 40 divided by 50 plus 40. So this is 24 ohms. So resistance in between these two terminals is 24 ohms. And in that case, next we can easily see that total resistance across terminals A and B will be equal to 6 plus this resistance, that is 24 plus 30. So this will be 6 plus 24 plus 30. This is 60 ohms. So now we have RAB, that is 60 ohms. So for total current, we can again use this formula for that. Total current is total voltage divided by total resistances. So this is 240 divided by 60. So this is 4 ampere. So this will be the actually current that is being supplied for the 240 volt source. Let's see another example. Consider the following circuit. Use delta Y transformations to find the voltage V. So here we have a complicated circuit. We want to find the voltage across 35 ohm resistance, and we need to use the delta star transformation. Again, you can observe that there is no resistance that is either in series or in parallel with any of the other resistance. Just like 20 ohm resistance, it is not in parallel with 12. Similarly, this 12 is not in parallel with 35. This 30 is not obviously in series or in parallel with 15 or 10 ohm resistance. So we cannot use series and parallel resistance equations, but we can use delta star transformations. So you can see that we have y here or T network here, we could convert that T network into corresponding delta network and so on. So let's see, convert the delta ABC into star networks. So again, we can see that actually we have A, B and C. This is actually delta network. So we can convert that delta into corresponding star network just like this. So we have actually point C here, point B and point A here. So we can convert or replace that network using this network. Here R3, R2 and here is R1. So we can easily find R1, R2 and R3 because we have the equations. Let's find the equivalent wire resistance marked in the circuit shown. Just like we want to find R1, R2 and R3. So we know that R1 is RB, RC divided by sum of the networks. So this is actually 5.71. Similarly, R2 is 4.7 and R3 is 2.85 ohms. So we can now replace this circuit or that delta using this Y network. Now you can see that this R2 is in series with 30 ohm resistance. Similarly, this 15 ohm resistance is in series with R3. So we can simplify. So clearly 15 ohm and R3 are in series and 30 ohm and R2 are also in series. So we can combine these two, and one more thing, you can see that 15 and R3, their equivalent is actually in parallel with 30 and 30 in series with R2. So we can say that 15 plus R3 it is in parallel with R2 plus 30 ohm resistance. So their equivalent resistance is in obviously series with R1. So we can say that resistance up to 35 ohms, that is actually in these two terminals will be called R1 plus parallel combination of these two, that is R1 plus 15 plus R3 in parallel with 30 plus R2. So this will we can simply plug the value of R3 and R2 here. So this will be actually 17.85 in parallel with 34.762 and plus R1. So we can simplify because remember that equivalent of two parallel resistances a product divided by sum. So this is product divided by sum. So finally we can simplify this as 17.511 ohms. So now we can redraw the circuit. This is actually a resistance from this terminal to this terminal 17.5. Now we can see that actually we can easily find V, that is voltage across 35 ohm resistance. Now we can determine the equivalent resistance of the parallel resistance of 35 and 17.5. So obviously this will be 35 in parallel with 17.5. So this is 11.672 ohms. So now you can see that this 100 volt is actually being divided between 16 and 11.67 ohm resistance. So we can use voltage divider rule here. So V will be equal resistance divided by sum of the resistance multiplied by total applied voltage. So resistance is 11.67 divided by sum is 16 plus 11.67 multiplied by 100. So this is 42.18 volts. So this is how we can use the star delta or delta star transformation. Thank you so much.